Hi, Professor Huckabee here. This is a lecture from last semester on Chapter 5. This is the first half of that hour and 15-minute long lecture. Just so you know, there is music in the beginning of the lecture because I had the RS chemistry site pulled up as I started, and it was playing on the computer, and I didn't know that it was on the whole time, basically. If you hear music in the beginning, that's why, and it gets shut off a little bit into the lecture. So with that, please enjoy. Also go to RS Chemistry if you want. It's a great site. And without further ado, here is your to-do list. So that is to do the homework 5 assignment, read chapter 5, start working the chapter 5 problems, and please see me or contact me if you have any questions, concerns, or need anything from me. So with that, I wish you all luck, and thanks.
Good afternoon. Can you hear me in the back? Maybe yes? It's fine? All right, cool. What do you think? All right, I'm not seeing any head shaking, so that's a good sign. All right, welcome everybody to Thursday lecture. Thursday lecture 1 week before the exam. As you see here, we have our classic silly meme slide to get you thinking about chemistry at the beginning. This one was submitted by one of you all, which I very much appreciate. If in the future you ever feel like you just have some creative meme energy you have to get out, feel free to email me something, and maybe it'll go up on the board. Right now, it was just the one, so it was very easy to say, that's a good meme, let's put it on. But with a little competition, who knows what would happen. So feel free, if you are so inclined, to draw some memes and have fun with organic chemistry. Okay, now for the thing to actually think about before class. Last time we kind of introduced the idea of chirality and of isomers, stereoisomers. And the question was, I gave you a few examples of one of these things is good, one of these things is not so good. But we didn't really talk about how you actually go about separating them. Because let's say that you are a doctor and you find out that, like in the case of last week, maybe the S version up there is what you want, but the R version really causes a problem. You have to be able to separate those so you can prescribe the right medicine. We're going to talk about later on in this lecture how you would actually do that, but hopefully you realize that that is kind of a big problem, because otherwise these two molecules are the exact same, right? Besides the fact that they're stereoisomers, they should have more or less the same boiling point, more or less the same melting point. Some of you all might be in the laboratory course, 231 or whatever it is. You've done a recrystallization, maybe. Maybe these things even make the same crystals. It's really hard to say. So how would you go about separating them? It's a big problem the world over. In fact, a lot of money is made in figuring out how to separate chiral molecules from their isomers, their enantiomers even. Where we left off was with assigning R and S the rotational configuration of stereoisomers, and the way we were doing that was with our really fun game, from RS Chemistry. So I thought instead of starting off with me writing more structures down, we would just do the game a couple times. That way we could all remember how to do this. So this is from their Learn, and I think this is on Hard because we're super experts now, and we can all do this together. So in this molecule, which apparently is responsible for how it smells after it rains, which is kind of cool, there is a chiral carbon here, the one with the star. That's the one they want us to work with. So let's all assign priorities to those together. So which one of these is the most important? All right, I heard it. I heard oxygen. Good. Yes, oxygen is the most important here. So there we go. Now, what is the most important? Good. Okay, yeah, carbon, that is true. This is a very serious tiebreaker we're talking about here, because they're all carbons, right? So let's think about the types of carbons that we have here. We have, I'm going to just draw it real fast. There we go, there's one ring, and here's another. Good, this one's like a wedge. So we have this CH3, and we have this CH3. So we're dealing with this carbon, and this one. So we're looking for, first off, the one that has the most not hydrogen bonds, right? So the most not hydrogen bonds. That's a dumb way to say that. We're looking for something with the least hydrogen bonds. And the one here that I have circled in red and blue, that one has 2 carbon bonds here and here, and 2 hydrogen bonds, because we don't see them, but bond line drawing says that there are 2 implicit hydrogen bonds there. The other 2 have 3 bonds to carbon, right? So they automatically have less H's. So that means this carbon that we had circled in red and blue must be the 3rd priority, the fourth priority, the least important. That's got to be 4. So let's drop 4 on there. Boom. All right, so 2 and 3. What do you guys think? That's pretty hard, right? This guy has 3 C's, 1 H, this one 2. So now we have to go into overtime. Overtime tiebreaker, sudden death. Which way you want to go? Do you want to go away from this mess over here? On this, we'll look at the top one first. Because one side over here has 2 hydrogens, 2 carbons, right? This guy. And then this one with the oxygen, because I didn't draw it in, has 3 carbons and 1 oxygen. Whereas the guy on the bottom, both of his neighbors have 2 carbons, 2 hydrogens, and this one has 3 carbons and 1 oxygen. So my question to you is, what's the winner? I think it is the one that has 2 neighbors, or sorry, 3 total neighbors, because if you look closely, I was really hoping somebody was going to catch me, but I might have been going too fast. He does not have, this one, the one in red, does not have 3 carbons and a hydrogen, right? Look closely, make sure you see it. There are not 3 carbons and a hydrogen, there are 4 carbons. 1, 2, 3, that's this one. This one, 3 and 4. 4 carbons, which means he is the second priority. So we'll throw him in there. That one's 3. All right, so we did that. It looks like it's happy with us so far. Now let's do the new projection. So imagine 4 is in the back. So 4 we have pointed away from us, and we're supposed to imagine where 1, 2, and 3 are. Okay, so everybody take a second and try to imagine that. Imagine visualizing you're looking down this bond here. Okay? Put in your mind where you think 1, 2, and 3 are. This is not easy. I think I got it. What about you guys? Some maybes, some questioning. I like that you're all trying though. You're all looking at least. All right, good. I think 1 is here. You all see that? Okay. No? If you're looking down at 4, imagine you are the blue asterisk. And you're looking towards 4. The O is pointed away from us as this molecule is drawn. but it looks like if you were the blue asterisk, the O would be to your left. So then it looks like also number 2 would be to your right, if you could imagine that. And then number 3 would be directly above you. So we're the blue asterisk. We're looking straight towards that number 4 carbon. To our left, we have the oxygen. Above us, we have number 3. So what is that? We're going, what? Counterclockwise? Counterclockwise is what? Raise the hand that it is. That's right. S for L, R for right. Okay, good. This is going to be a challenge. Can I see you and not think right? That's going to be good. All right, good. I think I'm seeing left hand, if I'm reading this right. Good. I'm seeing left hand. So that is S. We are awesome. Look at that. We all did it. Awesome job for us. And look at all these things we have to think about. All these ties. So good job, guys. So now that we're all proficient at this, I think we can move on to the next session in chapter 4. So please, again, if you're having a problem with this, feel free to play around on this site. It's pretty fun. Now we can assign R and S to enantiomers. But there's a really kind of fun history lesson that comes from this very specific thing that we're learning about right now. Because back before people even knew that organic chemistry existed, people were starting to figure out that molecules, if you dissolve them, could rotate light based on if they were chiral or not. And they didn't understand that's what it was, but that's how they started. And remember how when I showed you those 2 pictures at the very beginning of the lecture, and I was thinking, you know, how do you separate these 2 things? They're exactly the same. Well, Louis Pasteur in his laboratory one day happened to have a sample of tartaric acid from a local winemaker. This local winemaker had a lot of tartaric acid because in that region, the wines they were making was just chock full of it. And it would fall out and it would precipitate from solutions in the wine barrels, and they would call them wine stones. And Pasteur was very interested in this because they were a crystal that came out of something from a natural source. You know, again, chemistry was still in its early stages, and this just seemed like a really cool thing to them because they knew of minerals and they knew of living stuff, but it was very difficult to really understand about how those 2 things were linked. They couldn't just use some instrument and figure out what types of atoms were there. You know, they were still using like regular microscopes and stuff to think about chemistry. The good news for Louis was that his microscope was really useful in this case because whenever he had those crystals under the microscope slide, he found out that 2 of them had different shapes. And he could physically, with tweezers, separate them into one into another pile. And when he dissolved those 2 separated piles in different solutions and measured them using a polarimeter like this, well, where am I? Like this shown up here on the right, he found that one of these crystals rotated light to the, well, this is left for you guys, and the other one rotated it to the right. He didn't understand why, but that's what he found out. And that's because crystals, or organic material that is chiral, rotates light. It rotates light in general, but you can't really predict how strongly or in what direction. Okay? So that's why they're showing you these 2 pictures in very vague terms. Because you measure polarity, or how much they rotate light, by taking regular non-polarized light, first polarizing it, and then passing it through a solution of your material, and finding out how far you have to turn this slit here, how physically far you have to turn it to start seeing the light again. Because it really is like a twisting of the light. It's a really cool experiment. I hope you guys get to do it one day. It's an old, now in modern chemistry we don't use it as much because it's less useful. But it's really nice to be able to just turn the knob and like have nothing and then all of a sudden brightness. Like it's really pleasing. But it's a useful way to find out if something is chiral, and if you know how much it's supposed to rotate light, you can know if it's pure as well. In organic chemistry, there's a whole field of people in what's called asymmetric chemistry that are really into figuring out exactly how much these molecules are supposed to rotate light. Ooh, sorry. And there's some formulas in your book that talk about how to find the specific rotation. I'm just going to cover this quickly because it's not something that we are going to really focus on, but I think that you should be aware of it. So I think that you should read that part in your book about specific rotation, nothing else for the fun story about Pasteur, because I think they might have a little more detail there. But essentially, the rotation, we give it the Greek letter alpha. And you can find that nowadays, or you can find it. Nowadays, modern organic chemists, we have standardized how you normally report this number, and you report it by saying that the rotation over the concentration of your solution and how physically long the path is the light is traveling through is, the product of that gives you the specific rotation. And they do this because the specific rotation, how strong the light is rotated, also depends on how many molecules are in there. So we have to account for these things. And I'm not going to go through much more than that, actually, except for one little thing. All right, number one. Great. You know, I don't even think it happens at the same time every day. Have you noticed that? It's totally random. Same time? Okay. Well, that makes me feel better, I think. I'm not sure. I've been watching a lot of Office lately, so I feel like I'm just being pranked, you know? Right, so the only thing I want to really tell you, oh no. Okay. That one's done without comment. Right, the only thing I want to tell you about specific rotation is that if you have two enantiomers, two stereoisomers, they will actually rotate light the exact opposite way. So if you have this molecule versus this one would be, say, positive 23 degrees. The degrees means, again, how much you physically have to turn the dial to make the slits line up. And the other one would be negative 23 degrees. And the cool part of this is we see this type of stuff all the time in our daily lives, maybe not all the time, hopefully, but we don't realize it because a lot of the way that pharmaceuticals are named are using these specific rotation numbers. Because if something has a positive in its number, it's typically called dextrorotatory. And that you'll find that in medicines that have dextro in front of their name often. The same thing goes for, not same thing, if something is negative, we call that levorotatory. You might have seen some drugs that have levo something as their official name that they're given. So this is something you will still run into today. And the really weird thing is, because you can't predict what direction a molecule will twist the light, these have absolutely nothing to do with R and S. Nothing. It's a completely separate physical entity. You couldn't say, oh, that's levo something, that means it's S. No, you can't. Just a little aside for specific rotation. Yeah. Oh, if you still need that, there it is. Okay, yeah. All right, the other small thing that people who really study chirality and how to purify chiral materials is something called enantiomeric excess. And this is exactly like it sounds. This is basically how much of one stereoisomer do you have in excess of the other. So it's very simple, not even algebra. Maybe it's algebra. So if you have 50% of one, 50% of the other, you don't have excess, just by definition. They're 1 to 1. So your enantiomeric excess is 0. However, as soon as you start having a difference, say 55% of R and 45% of S, well, that's a difference. And in fact, that's a 10% difference, which is what your enantiomeric excess, also called EE, would be in that case. It's really simple. It's like, as a concept, it's not very difficult to understand, but it matters a lot when you're talking about whether you have 99.9% enantiomeric excess or 99%. It matters a lot. For chemists who care about this type of stuff, it matters a lot. And you can find this with a simple math formula that looks like any type of excess formula, which is, you can find this, from the specific rotation, because you know that one should go one way and the other should go the exact opposite way. So if you're given any value in between, you should be able to say this specific rotation I'm observing over what it should be pure times 100% also gives you the enantiomeric excess. Yeah, that's really all there is to say about that. Because the closer to this pure number you have, the closer to 100% you'll have, because you'll have one enantiomer only. All right. Different type of isomer. So we talked about so far constitutional isomers and stereoisomers, right? But we are not done, because there's several other types of isomers. Here are a few more. These are isomers that are also asymmetric. You have cis-trans isomers. We talked about this in terms of hexane, but it turns out alkenes do the same thing. If you have two alkenes, and you have, well, you have this one, and then you have this one. Ooh, that's bad. Don't do that. There we go. It's clear that those are different, right? But the big difference here is not that they are mirror images and non-superimposable, because if you put the red structure on top of the blue one, it still wouldn't match up, just like it would for the stereoisomers. But they're also non-mirror images. So this is a legitimate form of chirality that breaks that original mold that we set with stereoisomers. Because in stereoisomers, you could put a mirror plane in front and you would still have what looked like the same molecule. But you don't have it in this case. So they're not mirror images and they're not superimposable. These are called diastereomers when they are not mirror images and not superimposable. So we have, so far, constitutional isomers in the blue box. And then we had stereoisomers, which is a very broad term. We broke that into enantiomers, which were stereoisomers that were mirror images and non-superimposable. And now we have diastereomers, which cover a whole range of things that we're going to start talking about now. So these are two diastereomers. And while these are easy, we're going to bypass them directly and go directly to the harder stuff, because that's always fun. But no, seriously, we'll come back to this in a second, because in the realm of thinking about enantiomers, this is a good time to dive into what happens when you have, perhaps, a molecule with two different chiral carbons. Because now you have to think about both of them. And if you start drawing these structures that you could have, You could have one where they're both of these oxygen and chlorine are kind of coming out. You could have one where both of them are going away from you. So that's OH. This one is chlorine. And then you can have the two where they are different. And each of these is a unique molecule. So once you start adding the number of chiral carbons that a molecule has, the number really gets larger much quickly. Very quickly. Much quickly, very strong. In fact, there's a mathematical relationship that deals with how quickly the number of diastereomers increases along with chiral carbons. Because now, here's an example where you have 3 chiral carbons, and so now you have 8 potential diastereomers that you could be working with. Each of these, stereoisomers, each of these is either an enantiomer of another or a diastereomer of another. So 3 chiral carbons gives you 8. 1 chiral carbon gives you 2 sets, and 2 chiral carbons gives you 4. There's a mathematical formula there, and that is 2 to the n, where n is the number of chiral carbons. So then you could say, if you had 4 chiral carbons, you would have 16 different stereoisomers. If you had 5, you could have 32, and so on and so forth. Sounds like kind of a trivial thing, right? Except the great thing about organic chemistry is that we have so many good examples of weird molecules just in our own bodies. Cholesterol. You see commercials for this or for medications that lower this all the time. In fact, there are 254? I thought it was 6. I might have wrote that down wrong. Yeah, it is 256. I don't know why there's 4 there. 256 potential stereoisomers of cholesterol. I mean, look how many chiral carbons there are. You can see everywhere where there's a wedge or a dash, that indicates that there's a chiral carbon there because you need to know where that group is. So, you have 1, 2, 3, 4, 5, 6, 7, 8 potential centers, and there must be more? 2 to the 8th? Is that 256? It might be. Yeah, I think it is. So 8 chiral carbons gives you 256 possible stereoisomers, but what's really weird? Your body only makes this one. Out of all of them, this is the only one that we actually use. So my question for you is, why? Why is it that we only use the one? Are all of them not useful? Definitely something to think about, because we're talking about, we're just drawing structures up here. So many diastereomers possible up there. Are there medicines out there that could be derived from stereoisomers of cholesterol that we haven't found yet? Maybe. It's really hard to say. I'm not going to give you the answer. I'm just going to leave you with that. Which one is this? I think it's in this pile. Yeah. Oh no, wrong pile. There we go. All right, so going back to a slide from before about the diastereomers and the stereoisomers, something else weird about chirality kind of comes out.